This video is to demonstrate the BeachBall function that has been added to the version 3.12. As you can see here, I have a whole bunch of events and I have the moment tensor calculated before I display here, and I can choose to display the events in terms of the BeachBall. This is a typical way of displaying the moment tensor solutions in seismology community. Different events usually, or different group of events usually have different moment tensor solutions, and therefore the BeachBall will be slightly different. From an engineer point of view, a better way actually to display the failure mechanism is through this alternative way, such as the FMPlay. So as you can see, multiple sets of planes are displayed at the location where you have a recorded microseismic events. The size can be correlated to the magnitude or the signal-to-noise ratio of the event. In this case, this is corresponding to the signal-to-noise ratio. The alternative way that you can use is the DFN Disk, as you can see here. So instead of a rectangular shape, you now have a ellipsis. And the size of ellipsis again is correlated with the size of the microseismic events, which could be the magnitude or signal-to-noise ratio or any other parameters that you prefer to display. Obviously the quality are not the best because I choose to use a relatively low quality, but you can also increase the quality to make it a more ellipsoidal type of shape. The longest axis corresponding to the rake, and that actually corresponding tells you which direction these two planes, the relative displacement across the two planes. Now, the other question people may ask is, how do I come up with the moment tensor solution? How do I calculate the failure mechanisms? In Insight, there's two ways to do that. One is the typical moment tensor inversion, that each event you record the amplitude and then you do the matrix inversion and you get a moment tensor solution for that event. And that requires a relatively large azimuthal coverage. And if you don't have that, you will expect large uncertainties in the moment tensor solution. So the alternative solution, when you don't have a adequate azimuthal coverage, we recommend the VMS DFN. So we have different approximations. The method 3 has no approximation. Method 1 is the fastest, but also has some more approximation to speed up the process. For a number of events, as you see here, about 1,000. Method 3 may take a relatively long time, but don't worry, we have a parallel version included. If you check this box, you can do parallel processing and that can speed up the process. And as I'm showing you here, this is done by the MSDFN method. And I group them by time instead of by the location. But the alternatively, you can group them by location, and I'll show you how to do that in a moment. First of all, turn that back to the sphere. So that's the spheres, and that's the typical processed events that you can see. Now, based on the number of events, you can generally see two groups of the events. One is at the bottom, and the other group is on the top. And you can, based on that location, to calculate MSDFN. But if you want to be more accurate, you probably want to use the collapse events function. So the collapse event function is to perturb the location of each event within their location uncertainty and also collapse them towards the centroid. So this location actually has the same location uncertainty as the previous one. I can toggle it on and off. So you can see the events are actually has slightly different spatial locations. For the top group, you probably are able to see there are actually 3 distinctive structures that has been reviewed. So you can, based on that location, and calculate 4 different set of MSDFN, and you can get the moment tensor for each event and then display them as the in terms of the moment tensor solution or using DFN plan or DFN disk.